So let's discuss the example number one of resonant pulse inverters, series resonant pulse inverters with unidirectional switches. So this is the inverter that we discussed earlier, and in this one these are the values that are given to us. Input voltage is 220, 6 microfarad capacitor, 2 ohm resistor, and both inductors, of course, they have the same value, because remember, we want the circuit to be underdamped in both conditions. That is, when Q1 is on and when Q2 is on, it has to be underdamped with the same value of alpha, same value of omega naught, and same value of omega n, and then your waveform in the positive cycle and the negative cycle will exactly be the current waveform. So what I did, I entered all the values in octave, calculated the output frequency is given to us 7 kilohertz, and transistor turn off time is given to us 10 microsecond. So I calculated the angular frequency output, which is 2 pi f out, of course, and then I calculated resonant frequency, square root of 1 over LC. I calculated Napier frequency, R over 2L, and calculated the natural resonant frequency, which is a square root of omega naught square minus A square. The first question is to calculate dead zone. That is when both the transistors are off, and the dead zones is calculated using the formula that we discussed in the notes, which is right here: pi over omega out minus pi over omega n. So pi over omega out minus pi over omega n, it is off for 13.423 microsecond when both switches are off. Second is, what will be the maximum output frequency of the inverter? And again, we discuss the formula, which is, again, let's go back. This is the maximum output frequency, 1 over 2 times the turn off time of transistor plus pi over natural resonant frequency, and that came out to be 7.35 kilohertz. And observe that the output frequency is 7 kilohertz and the maximum frequency allowed for the inverter is 7.35. That means our output frequency is less than the maximum, hence the circuit is going to operate properly. Peak to peak capacitor voltage. So if we go to the capacitor right here, voltage, VC1 is the positive peak and VC, negative VC, is the negative peak, and both VC1 and VC equations to calculate those were discussed. VC is this and VC1 is this. Also remember, VC1 is VC plus VS right here. VC1 is VC plus VS. So all we need to do is to calculate VC. Of course, we know VS is 220 and we can calculate VC1. So we go ahead and calculated VC from the equation, which came out to be 100 plus 443. We calculated VC1, VC plus VC. So the peak to peak capacitor voltage will be VC1 minus negative VC, which was the negative peak value. So the peak to peak voltage is 420 volt. Peak load current will happen at the time when the output is peak. We calculated the time. The equation is 1 over omega n times tangent inverse of omega n over alpha. So the time at which the peak current is going to happen, I1, is 22.47 microsecond, and at that time we plug in this value in the equation of I1, and the peak current value is 70.8204. RMS value of the output current. Now the output current equation is this. It is an exponentially decreasing sinusoidal function. It is hard to calculate the integral of this, actually the square of the integral of this. Even the integral is hard to calculate, but the square of that is even harder. Now observe that to calculate the RMS value, I'm going from 0 to T1M, only the first part of the time, and I'm doubling the output. I'm doubling the integral. Why? Let me go back to the waveform again, and I think I discussed it in the class as well. Observe, since this and this are same, and when you take the square of the waveform, of course the negative cycle is going to go in the positive cycle and they will exactly be the same. So it only makes sense if we just calculate one area and then double the amount of that, and that's going to be the area of both the cycles. Of course, integral is just calculation of the area, and that's what we are doing over here. We are calculating one area, square of the signal, one area, and then we are taking the double of that, and of course we divide the whole thing by the output time to calculate, to do the root mean, and then take the square root to calculate the root mean square. So we did that. I did that using MATLAB. I guess I discussed it. MATLAB has a function integral for fixed integration or limit integration, and all you have to do is to write down the function as in the array format. So anytime you have multiplication and power and division between the two vector, of course t is a vector, then you have to put a period. So you write down the equation of I1 square and then integral of the function, which is this. Of course variable of integration is t, so we write down like this at t, and the equation in terms of the array function, and integral of f from 0 to t1m, and we have already calculated t1m, which is 58.055 microsecond. Observe that an interesting fact, 58 is the total time period of t1, which is the first cycle. So this is 58, come on, this is 58 microsecond, and we calculated the peak time where the peak will happen, and it is not the half of t1. It is not 58 divided by 2, which is 29. Rather it was what, let's see, peak time right here is 22, so it's less than 29. As we expect, that is not a pure sinusoid. Remember, it's exponentially changing sinusoid. So the peak happens before the half of the time period. Remember that. So the peak time is 50. The total time is 58 microsecond for t1, and we integrate that. And then this is my integral value, 138 milli, which is this integral right here. This is 138 milli, and then I'm gonna go ahead and multiply that by 2 divided by t out and take the square root of that. So right here I multiply it by 2 divided by t out, take the square root of that. So the RMS value of the output current is 44 ampere. Active output power is RMS current squared times R. We know the value of R is 2, so we can calculate the active output power, which is 3.88 kilowatt. Average supply current. Now the supply current, source is supplying current only when during mode 1. There is no current in mode 2, and of course mode 3 is source free mode. So the supply current is only coming in mode 1 for the whole cycle. So we go ahead and use the average value, average formula, 1 over T out, 0 to T1M, and the current. And again I used Octave or MATLAB, whatever you want to use, and use integral to calculate the average current, which is 17.677. RMS current of each switch. Again, each switch is this current is passing through each switch right here for the whole cycle. So we calculate the RMS current of each switch, which will be 31.1809, and that's the end of example number 1.